Good afternoon. My name is Edith Garcia, and today I will be presenting substitution. In this section, we expand our ability to compute antiderivatives by developing a useful technique called integration by substitution. This method gives us a process for helping to recognize a whole range of new antiderivatives. We will begin our lesson with substitution with indefinite integrals. Here I have provided the general definition of substitution for indefinite integrals. This definition basically states that you want to choose a new variable, let's say u, for the innermost expression or the inside term of a composition of functions that you want to evaluate. Then you want to compute the derivative of that u function. We replace all terms in the original integrand with the expressions involving u and du. Once we have the new integral, we want to evaluate the resulting u integral. If you still can't evaluate the integral, you may need to try a different choice of u. Once you have the correct choice of u, you want to replace each occurrence of u in the antiderivative with the corresponding expression in x. We always want to keep in mind, though, that finding antiderivatives is the reverse process of finding derivatives. On here we have an example for the indefinite integrals, and we want to evaluate x cosine x squared dx. Notice that the derivative of x squared is 2x. Unfortunately, we don't quite have a factor of 2x in the integrand. This does not present a problem though, as you can always push constants back and forth past an integral sign. Notice that we can rewrite the integral as 1/2 integral 2x cosine x squared dx. Once we factor out the 2, we would eventually get back the original function we started off with. This will provide us the correct u substitution for x squared, so that du becomes 2x dx. So that we have 1/2 the integral of cosine u du. Taking that out of the integrand, we have 1/2 sine u plus c. C represents the constant. And once we have the actual evaluation of the integral, we want to replace back the original x function for u. And as you can see that right there, we replace u for x squared. And of course, because we want to make sure that our work is correct, I went ahead and provided the checking of our derivative. So here we take the derivative of 1/2 sine x squared. We notice that the derivative of that is 1/2 cosine x squared times 2x, which is the derivative of x squared. And then, of course, again, the 1/2 and the 2 cancel out, which gives us back the x cosine x squared, which in this case is the original integrand. Next, we're going to be discussing substitution with definite integrals. There's only one slight difference in using substitution for evaluating a definite integral, and that is that you must also change the limits of integration to correspond to the new variable. The procedure here is then precisely the same as that for the indefinite integrals. The only exception being that when you introduce this new variable u, the limits of integrations change. So instead of going from x equals a and x equals b, now the new corresponding limits will go from u of a and u of b. Or in this particular definition that we have here on the screen, g of b and g of a. So next, I provided you with an example for definite integrals. And based on this example, you want to look for terms that are derivatives of other terms. Here we notice that the derivative of the exponent, negative t squared over 2, is equal to negative t. So this is going to be our new variable, or our u substitution. And so when we compute the derivative of negative t squared over 2, we get that it's negative t dt. And of course, we do have to change the limits. So for the upper limit of integration, u of 15 gives us negative 225 over 2, and for t equals 0, u of 0 gives us 0. So at the very bottom integral, we can see that we replaced all the t and dt variables with u and du, and we already adjusted our limits, both upper and lower limits, with our new u of a and u of b variables. So once we actually evaluate the integral, we get that our answer is negative e to the negative 112.5 exponent plus 1. Now, it may have occurred to you that you could use a substitution in a definite integral only to find an antiderivative and then switch back to the original variable to do the evaluation. Although this method will work for any problems, we recommend that you avoid it for several reasons. First, changing the limits of integration, it's not very difficult and results in a much more readable mathematical expression. And second, in many applications requiring substitution, you will need to change the limits of integration. So you might as well get used to it now. Now, on this next slide, I have provided you a link to the Khan Academy where they provide you with plenty of examples in video form, of course, of U substitutions. And of course, they expand on their examples. They go into natural logs, all these other more complex U substitutions. So whenever you have time, please make sure you visit khanacademy.org so you can see this other U substitution techniques. Now here I have provided a more interactive evaluation of the integrals by using substitution. On the left side of the screen, I have the graph of the function cosine squared of x times sine of x, and on the left side I have the graph of negative sine x. Now we are going to be comparing the area under the curve of each of the functions, which we'll notice that they're exactly the same. Now, because we are studying substitution, we are going to use cosine x as our function that we're going to replace for u. So that means that the derivative of cosine of x is going to now be negative sine x dx, and we're going to label that as du. So when we actually do the u substitution, this is what the integral will look like, negative u squared du. And because we do have to change our limits, because we're doing this new variable change, we're going to have our limits go from u of a to u of b, which in this case, I have them set up as negative pi over 2 and pi over 2. And of course, here I went ahead and already provided you what this integral evaluates to. In this case, for this specific values a and b, it's going to be 0 because it is an odd function, and odd functions automatically cancel each other. But of course, if we move our a variable or our a interval, we notice that our area changes. In this case, we only want a certain certain area going from 0 to pi over 2, and that area under the curve is 0.33. And as you can see, both functions stay exactly the same with the correct u substitution. That doesn't change. The only thing that we're changing are the upper and lower limits. And in comparison with the other graph over here, we can see that that corresponds to the same area under the curve of the du function as well. We can also move that b variable, and we notice that our area under the curve also changes. It increases, decreases, it becomes 0 at certain times, and that's basically our lesson for today. Thank you for assisting my presentation. See you next time.